Hello there and welcome back to the Sleep Science. Tonight you're standing barefoot on solid ground. Maybe your bedroom floor, maybe the quiet soil outside in your imagination. And beneath you the planet is humming. Not metaphorically, not poetically, literally humming. A faint, steady pulse is traveling through thousands of kilometers of rock and metal, slipping beneath oceans, threading through continents, brushing past tectonic plates like a shy underground whisper. You can't feel it. You can't hear it. But instruments can. And if you were down there several hundred kilometers below your comfy mattress, you probably wouldn't survive this. The pressure alone would flatten you into a very thoughtful pancake. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, tell me your location and the local time where you are. I love imagining this strange planetary murmur stretching under cities, deserts, forests, and wherever you happen to be listening. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The signal was first noticed not because the Earth shook violently, but because it didn't. Around the early 2000s, sensitive seismometers, those incredibly patient machines that spend their entire lives listening to rocks, picked up something peculiar. Instead of the sharp jolt of an earthquake or the chaotic rumble of tectonic plates grinding, there was a steady, repeating pulse. It moved through the planet at regular intervals like a calm, cosmic metronome. You imagine scientists staring at their monitors, coffee growing cold, as thin lines on screens bounced with unexpected rhythm. Seismology as a formal science dates back to the late 19th century, after devastating earthquakes pushed researchers to better understand Earth's vibrations. In 1889, the first modern seismograph capable of detecting distant earthquakes was developed in Germany. Since then, global networks have formed, thousands of instruments scattered worldwide, quietly eavesdropping on the planet's internal conversations. And yet this signal didn't fit the usual script. It wasn't tied to a quake. It didn't spike and vanish. It repeated, over and over, a pulse emerging from somewhere deep below, steady enough to catch attention but subtle enough to remain mysterious. If Earth had a heartbeat, this would be it, though thankfully much slower. Kind of because if your heart beat every 26 seconds, you'd be scheduling a very urgent doctor's appointment. Here's the strange part. The signal seemed to circle the globe. It wasn't confined to one continent. Stations in North America picked it up. So did instruments in Europe and Asia. Like a whisper traveling through a cathedral dome, it echoed around the planet's interior. Now, Earth is not silent. Far from it. Even when no earthquakes strike, the ground constantly vibrates. This phenomenon is called seismic noise. Ocean waves crashing against coastlines create tiny tremors that ripple inland. Wind buffets mountain ranges. Human activity adds its own jittery signature. Traffic, construction, even synchronized stadium cheering. Yes, your favorite sports team might literally shake the earth a little. Modestly. And let's not give them too much credit. But this pulse was different. Researchers began comparing timestamps. The signal repeated with uncanny regularity. Every cycle arrived almost like clockwork. Not chaotic, not random. Rhythmic. If Earth were trying to send a Morse code message, this would be a very slow, very dramatic opening. Historians still argue whether the first researchers fully grasped the anomaly's importance at the time, or whether it seemed like just another odd blip in a sea of data. Scientific discovery often works like that. Something appears strange, gets filed away, then resurfaces when patterns become undeniable. You drift deeper now, imagining descending through layers of rock. Beneath the thin crust where you walk, drive, and occasionally stub your toe, lies the mantle. In a vast expanse of semi-solid rock extending nearly 2,900 kilometers down. Temperatures climb into the thousands of degrees Celsius. Pressure intensifies until minerals rearrange themselves into exotic forms. It's less a fiery lava ocean and more a slow-moving, ultra-dense taffy, creeping at centimeters per year. And somewhere within or beneath this immense region, the pulse begins. A quirky tidbit, some early fringe forums online briefly speculated the signal might be a hidden underground city's power source. Yes, because obviously, if you're building a secret subterranean metropolis, you design it to emit a perfectly measurable seismic rhythm detectable worldwide. Subtlety clearly not included in the architectural plan. Back in the real world, scientists did what scientists do best. They doubted everything. They tested instruments for glitches. They cross-referenced data from independent stations. They compared signals during storms, calm weather, different seasons. The pulse persisted. You picture a lab at night, dim overhead lights, a map of the world dotted with blinking sensor locations, lines radiating outward from a mysterious focal point. The earth beneath your feet, so apparently solid, so reassuringly stable, is in constant motion. Tectonic plates drift roughly as fast as your fingernails grow. Convection currents churn slowly in the mantle. The liquid outer core swirls around the solid inner core, generating Earth's magnetic field like a colossal dynamo. Mainstream geophysics tells you the planet can ring after major earthquakes. In 2004, when the massive Sumatra-Andaman earthquake struck, WEST instruments detected the entire Earth oscillating for days, vibrating like a struck bell. That's a fact so astonishing it almost sounds fictional. But this signal? It wasn't triggered by a catastrophic quake. It appeared without a dramatic prelude. You lean back into the quiet of your room and imagine that even now, yes, right now, the pulse could still be traveling beneath you, through bedrock, beneath subway tunnels, under oceans and ice sheets, a planetary murmur threading through continents while you sip tea or scroll on your phone. There's something oddly comforting about it. The Earth is not a static stage. It's a living system of shifting layers and circulating heat. The signal reminds you that beneath daily routines, emails, laundry, existential dread, the planet is engaged in ancient, slow choreography. And yet, we don't fully understand it. That's the hook. That's the delicious scientific tension. Because when something repeats this consistently, physics usually has an explanation. But the explanation here is not simple. Not yet. The pulse invites deeper listening. So you stand there metaphorically barefoot on the crust, feeling nothing, but knowing that far below, in darkness older than any civilization, something is keeping time. And as we move forward, you'll descend layer by layer, following that rhythm into the mantle, toward the metallic heart of the world, where stone flows like syrup and iron spins in silent storms. For now, just notice the quiet around you. Notice how solid everything feels. And remember that beneath that calm surface, the earth may be tapping out a slow, steady beat, patient, persistent, and impossible to ignore once you know it's there. The pulse doesn't announce itself with drama. It doesn't crack walls or rattle dishes in your kitchen. Instead, it slips quietly into the records of machines designed to notice the nearly unnoticeable. You imagine a seismometer as a monk of the scientific world, silent, still, and deeply attentive. Its job is simple: detect motion, even the tiniest tremor, even the faintest shiver traveling through solid rock. Modern seismometers are astonishingly sensitive. Some can detect ground movements smaller than the width of a hydrogen atom, which is both impressive and mildly unsettling because it means the planet can sneeze in Antarctica and a machine in Alaska might politely log it. When the Global Seismic Network, coordinated in part by organizations like the International Seismological Center, links thousands of these instruments together. When something shakes, the world listens. That's how the signal first became impossible to ignore. Around the early 2000s, researchers reviewing continuous background data noticed a repeating oscillation. Not a spike, not a sudden burst, a smooth, rounded wave appearing at consistent intervals. It wasn't tied to any known earthquake event. No major rupture preceded it. No aftershock sequence followed. Just a steady, rhythmic pattern sliding through the noise. You picture a scientist scrolling through months of waveform data, lines rising and falling like minimalist mountain ranges. Most of it looks chaotic, random. But then there it is, a repeating bump, subtle, measured, predictable. Like someone tapping a spoon gently against the inside of a giant ceramic bowl. At first, it could have been dismissed as instrument drift. Seismometers, like all devices, can misbehave. Temperature changes, electronic interference, even local traffic can contaminate readings. But here's where it gets interesting. Multiple stations, thousands of kilometers apart, recorded the same pulse. When instruments in North America, Europe, and Asia independently confirm a pattern, you stop blaming the coffee machine in the lab. One mainstream fact anchors this moment in scientific history. Seismologists have long relied on triangulation to locate earthquake epicenters. By comparing the arrival times of seismic waves at different stations, they can pinpoint where a quake began. This technique, refined throughout the 20th century, revolutionized our understanding of plate tectonics. In the 1960s, seismic mapping helped confirm that continents drift, a theory once dismissed as fringe. So when a new signal appears globally, the instinct is the same. Triangulate it. Trace it back to its source. But triangulating this pulse proved tricky. Unlike sharp earthquake waves, which have clear starting points and defined wave types, P waves that compress, S waves that shear, this signal was more like a sustained oscillation. It didn't shout, "I began here." It murmured, "I'm everywhere." Historians still argue whether early interpretations underestimated how widespread the signal truly was because the first datasets were limited. Continuous monitoring wasn't always archived at the same resolution it is today. Some older systems only saved data when earthquakes crossed certain thresholds. Subtle, repeating background vibrations might have slipped through unnoticed for years. That possibility sends you drifting backward in time. What if the Earth has been pulsing like this for decades, for centuries? Before seismometers existed, no human would have known. It's humbling to realize how much of reality depends on having the right tools to perceive it. Before microscopes, microbes were invisible. Before telescopes, galaxies were myths. And before ultra-sensitive seismic arrays, Earth's faint rhythms went unrecorded. As researchers compared datasets, a pattern solidified. The pulse repeated roughly every 26 seconds. Not 25, not 30, around 26, regular enough to stand out. If Earth were a drummer, it would be playing an extremely slow, minimalist solo. Experimental jazz, perhaps. The kind where you nod thoughtfully and pretend you totally understand it. A quirky tidbit emerged during early investigations. One research team jokingly nicknamed it the microseismic heartbeat. The name didn't stick in formal literature, but it captures the mood. There's something strangely intimate about imagining the planet with a pulse. Of course, before anyone embraced poetic metaphors, they checked the obvious culprits. Industrial activity can create repeating vibrations. Massive machinery, oil drilling platforms, mining operations, even certain types of heavy manufacturing can generate cyclical seismic signatures. During the Cold War, seismometers were sensitive enough to detect underground nuclear tests, so if humans were responsible, it wouldn't be unprecedented. But the timing didn't match any known industrial cycles. The signal persisted across weekends, holidays, and seasonal shutdowns. It didn't align with known drilling schedules, and its strength didn't correlate with major population centers. If it were human-made, it was remarkably consistent and globally coordinated, which would require an absurd level of secret organization. And let's be honest, coordinating a group chat is hard enough, so attention turned back to natural sources. Seismology teaches that much of Earth's background vibration comes from ocean waves. When large swells collide, they create pressure variations that transfer energy into the seafloor, producing what's known as microseisms. This phenomenon has been well documented since the early 20th century. In fact, during strong storms, when the constant pounding of waves can make the ground tremble thousands of kilometers inland. The ocean, it turns out, is not content to stay in its lane. But ocean-driven microseisms usually vary with weather patterns. They grow stronger during storms and weaken when seas are calm. The 26-second pulse, however, displayed an eerie steadiness. It didn't fluctuate wildly with seasonal wave activity. You imagine scientists overlaying storm data with seismic graphs. Hurricanes sweep across oceans. Wave heights surge, and yet the pulse continues, steady as a metronome. That consistency deepens the mystery. Another open scholarly debate begins to take shape. Historians still argue whether the signal represents a single physical source or a resonance phenomenon, Earth amplifying an otherwise ordinary input into something extraordinary. Is it one hidden drummer, or the planet itself acting like a resonant chamber? The distinction matters. If it's a localized source, you can search for it geographically. If it's resonance, then the entire structure of the planet is involved, like a bell ringing at its natural frequency. You let that idea settle. The entire planet ringing softly, continuously beneath your feet. Outside your window, things feel still. Maybe a car passes. Maybe a refrigerator hums. Ordinary sounds. Ordinary vibrations. But beneath them, threading through bedrock and mantle, that steady 26-second rhythm may still be circling the globe, patient and unhurried. And now that it has been noticed, really noticed, there's no going back to ignorance. The seismometers are listening more closely than ever. The data archives are being combed. Why? The maps are growing more detailed. The pulse has stepped out of obscurity, and you, drifting deeper into this story, are beginning to follow it toward the parts of Earth we rarely imagine. The regions where rock flows slowly, iron spins silently, and mysteries keep remarkably good time. The first instinct, when confronted with a repeating vibration inside a restless planet, is simple. It must be an earthquake. Earthquakes are the celebrities of seismology. They arrive dramatically, shake the furniture, and then leave a long trail of aftershocks like gossip in their wake. But this pulse, it behaves nothing like them. You picture the classic earthquake waveform, sharp, jagged spikes as energy bursts outward from a rupturing fault. P waves arrive first, compressing rock like a spring. Then S waves follow, shearing side to side. Surface waves roll in last, often causing the most visible destruction. It's a well-understood sequence, mapped and categorized over more than a century of careful observation. The 1906 San Francisco earthquake, for example, helped establish foundational models of fault rupture and seismic wave propagation. Since then, each major quake has refined our understanding of how Earth releases stress. But the strange pulse doesn't fit that choreography. Instead of a sudden beginning, it eases in. Instead of chaotic complexity, it repeats with gentle regularity. No epicenter can be triangulated in the usual way. No fault line confesses. The waveform looks almost polite. Rounded peaks, consistent spacing. If earthquakes are cymbal crashes, this is a steady drum tapped softly in the distance. So researchers begin eliminating possibilities. When could it be cultural noise? Human activity creates what seismologists call anthropogenic seismic noise. Traffic surges during rush hour. Factories operate on cycles. Even coordinated dancing at large concerts has been measured in the ground. There's something charming about imagining thousands of fans at a stadium inadvertently helping geophysicists calibrate their instruments. But human-generated vibrations usually correlate strongly with population density and daily schedules. They ebb at night. They spike during work hours. The 26-second pulse does not clock in or out. You imagine scientists overlaying urban activity data with seismic readings. Cities sleep. The pulse continues. Holidays pass. The pulse keeps time. If it were human-made, it would require a secret, synchronized, a planet-wide machine operating without maintenance breaks, which sounds less like engineering and more like a science fiction villain's side project. And historically, humanity struggles to keep even daylight-saving time consistent. Next suspect, instrument error. Seismometers are incredibly sensitive, but they are not magical. Temperature drift, calibration shifts, even tiny electronic oscillations can create artifacts. So researchers compare different instrument types: broadband seismometers, short-period instruments, ocean-bottom sensors. They check stations run by different countries, built by different manufacturers. The pulse appears across them all. One mainstream fact grounds this phase of investigation. Modern global seismic networks are intentionally redundant. Multiple stations often cover the same region to ensure reliability. This redundancy has allowed scientists to detect even clandestine nuclear tests with remarkable precision. So when independent networks confirm the same signal, confidence grows that it's real. The signal survives scrutiny. Then comes the question of scale. Earth constantly vibrates from ocean waves colliding. These microseisms typically cluster around periods of 5 to 20 seconds. They are strongest during storms and most prominent along coastlines. The physics behind them is well studied. When two ocean wave systems interact, they create pressure oscillations on the seafloor at double the wave frequency. But 26 seconds? That's slightly longer than typical dominant microsystem periods. Close enough to be suspicious, different enough to be unsettling. Historians still argue whether early researchers were biased toward ocean explanations simply because microseisms are such a common background source. When you have a hammer, waves cause vibrations, everything can start to look like a wave-shaped nail. You drift mentally over the oceans. Vast storm systems churn in the North Atlantic. Swells travel thousands of kilometers before breaking. The ocean is a master of rhythm, generating tides under the pull of the moon, seasonal cycles under solar heating, and chaotic wave interference patterns. Could some unique configuration of underwater topography be amplifying a specific 26-second resonance? It's plausible, but the consistency remains puzzling. Another possibility enters quietly: harmonic resonance. Earth, like any physical object, has natural frequencies. Now strike a bell, and it rings at tones determined by its size and material. In 1954, after a massive earthquake in Alaska, scientists first confirmed that Earth can oscillate in whole-body modes, free oscillations that make the planet vibrate like a struck sphere. These modes can last for hours or even days after large quakes. The discovery was a triumph of mid-20th century geophysics. But here's the twist: those free oscillations require a major trigger. A powerful quake acts like the hammer. Without it, the bell stays silent. The 26-second pulse appears without such a hammer blow. A quirky fringe idea briefly circulates in online communities. What if it's a hidden, ultra-deep magma pump cycling at regular intervals? Or an undiscovered tectonic engine breathing slowly beneath the crust? These speculations aren't published in journals, but they capture the imagination. The Earth as a living organism, inhaling and exhaling on a half-minute timescale. Back in the labs, scientists adopt a more grounded approach. They analyze the waveform's spectral content, essentially breaking the signal into its component frequencies. The 26-second peak stands out in the spectrum like a persistent note in a symphony. Not the loudest note, not overwhelming, but stubbornly present. You imagine the graph: frequency on the horizontal axis, amplitude on the vertical. A small but sharp rise at around 0.038 hertz. That's the mathematical expression of the mystery. Dry numbers representing a planetary murmur. And yet, despite its subtlety, the signal's persistence is what makes it compelling. Noise is random. Patterns are meaningful. When something repeats this cleanly, pure physics is usually behind it. The open scholarly debate sharpens. Historians still argue whether the signal is best classified as a driven oscillation, forced by some continuous external energy source, or as a self-sustaining resonance within Earth's interior. The distinction is crucial. A driven system stops when the driver stops. A resonant system can amplify even weak inputs dramatically. You let that idea settle into the quiet space around you. Perhaps the Earth isn't being struck. Perhaps it's being gently nudged over and over by something steady. And in response, it hums. The more typical explanations fall away one by one. Not a standard earthquake, not routine industrial noise, not a simple instrument glitch, not easily explained by ordinary storm microsystems, which leaves you suspended in a comfortable scientific tension. Because when familiar answers dissolve, curiosity deepens. The signal remains, steady, patient, looping around the globe every 26 seconds. And as researchers rule out what it isn't, the question of what it is grows heavier, like descending further underground. You're no longer just listening to data on a screen. You're listening to a planet that refuses to be simple. By now, the number has started to feel oddly personal. 26 seconds. Not a neat half minute. Not a tidy quarter minute. 26. Long enough to take a slow breath. Long enough to glance at the clock and wonder if it's stuck. And then, there it is again. The pulse. You imagine the signal as a ripple that doesn't just radiate outward and fade, but travels around the planet, threading through crust and mantle, curving along the spherical interior like a train that never quite stops at the station. Seismologists begin referring to it as a 26-second microsystem, and the phrase sounds harmless enough, almost cute. But there's something profound about the idea that every half minute, Earth completes a quiet internal cycle. One mainstream historical anchor grounds this phenomenon. In 1960, after the massive magnitude 9.5 Valdivia earthquake in Chile, the largest ever recorded, scientists observed Earth's free oscillations ringing for days. The planet vibrated in multiple modes, some lasting nearly an hour per cycle. That discovery confirmed that Earth behaves like an elastic sphere capable of global resonance. It was the geophysical equivalent of realizing your house is actually a bell. But those oscillations required a catastrophic trigger. And the 26-second pulse does not. What makes this signal especially strange is its persistence over years. Not hours, not days, years. When researchers comb through archived data, they find it appearing repeatedly across seasons. Sometimes it strengthens, sometimes it softens, but it never fully disappears. It's as if the planet has a background rhythm section that never takes a coffee break. You drift across a mental globe, watching waveforms appear in sync at stations separated by oceans. The signal shows up in North America, it appears in Europe, it's detectable in parts of Asia. That global footprint suggests something large-scale, either a source capable of sending waves around the entire Earth or a resonance mode being excited continuously. And here the distinction becomes fascinating. If a wave originates from a specific point, well, seismologists can typically trace it backward. They analyze arrival times, they calculate travel speeds, they map probable epicenters. But the 26-second pulse behaves more like a standing wave, a pattern that seems to exist everywhere at once, rather than racing outward from a dramatic starting line. Historians still argue whether early interpretations underestimated the complexity of global standing wave patterns and continuous seismic noise. It turns out the Earth's background hum is far richer than once believed. In fact, by the late 1990s, scientists had discovered something called the Earth's hum, continuous free oscillations, excited not by earthquakes, but by atmospheric and oceanic processes. This was a major revelation. Even in the absence of catastrophic events, the planet gently vibrates at its natural frequencies. So perhaps the 26-second pulse is part of that hum? But here's the twist. The Earth's hum typically spans a range of frequencies. It's a spectrum, not a single metronomic beat. The 26-second signal stands out as unusually coherent, almost too clean. You imagine sitting in a vast concert hall while an orchestra warms up. Random notes drift through the air. Then suddenly, one violin begins playing a single tone at perfect intervals, over and over. That's the feeling the signal creates in the data. A quirky tidbit slips into the story here. At one point, a few curious observers wondered if the pulse might be linked to tidal forces from the moon. After all, the moon's gravitational pull moves entire oceans, raising tides daily. It even slightly deforms the solid Earth by a few centimeters. But lunar tidal cycles operate on hours, not seconds. If the moon were responsible for a 26-second beat, it would be working on an extremely aggressive schedule. Even celestial bodies need downtime. As researchers refine their analysis, they notice something subtle. The amplitude of the pulse tends to be stronger during certain seasons in the northern hemisphere. That hint nudges attention toward ocean activity in the North Atlantic, where powerful winter storms churn vast swells. This isn't a conclusion yet, just a correlation, but it's enough to redirect the searchlight. Meanwhile, the signal's stability continues to intrigue. In physics, sustained oscillations often require a continuous energy source. Think of pushing a child on a swing. If you stop pushing, friction slows the motion. For Earth to maintain a steady 26-second rhythm, something must be feeding energy into the system. And Earth is not short on energy sources. Solar heating drives atmospheric circulation. The moon drives tides. Internal heat from radioactive decay fuels mantle convection. The liquid outer core churns, generating the magnetic field. It's a dynamic planet, even if it looks like a calm blue marble from space. You sink deeper into the idea that beneath you, the mantle, stretching nearly 2,900 kilometers thick, is not rigid stone, but a slow, creeping solid. Over millions of years, it flows. Convection currents rise and fall like lava lamps operating on geological timescales. If resonance is occurring, it may involve this immense layer acting as part of a planetary-scale acoustic chamber. The open scholarly debate sharpens again. Historians still argue whether the 26-second signal represents a discrete resonance mode of Earth that happens to be preferentially excited, or whether it is simply the most visible peak in a complex interaction between ocean waves and solid Earth structure. In other words, is it special or just especially noticeable? That distinction matters because if it's a fundamental resonance mode, it tells us something intrinsic about Earth's structure, its density distribution, its elasticity, its internal layering. If it's externally driven by ocean waves, then it becomes a story about the restless surface coupling with the deep interior. You like that image? The ocean whispering to the mantle, surface storms tapping on the crust until the whole planet hums in reply. Outside your imagined window, just wind might be brushing trees. Somewhere, real waves are crashing against real coastlines. And beneath it all, every 26 seconds, a quiet cycle completes. Not violent, not destructive, just persistent. There's something almost meditative about it. A planetary breath, a reminder that stability and motion coexist. The ground feels solid because its movements are usually too subtle for your senses. But instruments, those patient, monk-like listeners, continue recording. And the more you think about it, the stranger it becomes. Because if a storm in one ocean basin can excite a vibration detectable across continents, then the boundary between surface weather and deep Earth is thinner than it seems. The planet is less a stack of isolated layers and more a connected system, where energy travels in surprising ways. The 26-second pulse keeps circling, and you, lying comfortably far from crushing pressures and molten rock, follow its rhythm into the next layer of mystery. By now, the ocean is impossible to ignore. You drift out over the North Atlantic in your mind, where winter storms gather strength like orchestras tuning before a dramatic performance. Winds howl across open water, transferring energy into waves that grow taller, longer, heavier. Some swells stretch hundreds of meters from crest to crest, rolling across entire ocean basins with slow, deliberate power. When they finally meet resistance, another wave system, a continental shelf, an undersea ridge, they don't simply collapse, they push. Here's a solid, mainstream fact. When ocean waves interact, especially when opposing wave systems collide, they can create pressure fluctuations on the seafloor at twice the frequency of the original waves. This phenomenon, described in the early 20th century and formalized by oceanographer Michael Longe-Higgins in the 1950s, explains much of what we call microseisms. In essence, the ocean's surface chaos gets translated into rhythmic thumps against the planet's crust. Usually those thumps cluster around periods of 5 to 20 seconds. But what if certain conditions, specific wave heights, precise interference patterns, unique underwater topography, favor a longer beat? What if somewhere in the vast North Atlantic, storms are playing the planet like a drum? Researchers begin mapping the seasonal variations of the 26-second signal. It tends to grow stronger during Northern Hemisphere winter, when Atlantic storms are most intense. And that correlation is difficult to ignore. It doesn't prove causation, but it nudges the needle. You imagine overlaying storm track maps with seismic amplitude graphs. Swirling low-pressure systems sweep eastward from North America toward Europe. As they intensify, the 26-second pulse brightens slightly on seismic records. The connection feels less mystical and more mechanical. And yet it's not that simple, because the signal doesn't disappear in summer. It weakens, yes, but it lingers. If ocean storms are the drummer, they are remarkably consistent performers. Historians still argue whether the Atlantic alone can account for the signal's global coherence, or whether multiple ocean basins contribute simultaneously, reinforcing a particular planetary resonance. It's possible that the Pacific, Southern Ocean, each one and even smaller basins are all feeding energy into the same natural frequency of the Earth. You pause over that phrase, natural frequency. Every physical object has one. Strike a wine glass and it rings at a tone determined by its shape and thickness. If you apply energy at just the right rhythm, even gently, the sound grows. This is resonance, the amplification of motion when input matches intrinsic frequency. Engineers worry about it in bridges and skyscrapers. The Tacoma Narrows Bridge collapse in 1940 is the classic cautionary tale. Wind-induced oscillations matched the bridge's natural frequency, and the structure dramatically failed. Gracefully, but dramatically. Now imagine resonance on a planetary scale. Earth's structure, crust, mantle, outer core, inner core, creates a set of possible vibrational modes. What some are triggered by earthquakes, others may be excited continuously by surface processes. If ocean wave pressure variations happen to match one of these modes around 26 seconds, the planet might respond like a bell being gently but persistently tapped. A quirky tidbit floats into the mix. In the early days of investigating the signal, a few curious minds speculated whether massive iceberg interactions near Greenland might play a role. After all, enormous ice masses grinding and calving can generate seismic signals. Some even propose that rhythmic iceberg collisions could act like slow metronomes. It's a cinematic image, glacial giants clinking like frozen champagne glasses. But data hasn't strongly supported that idea. Still, the fact that such theories surfaced shows how mysterious the pulse initially seemed. Back in the data, researchers performed beamforming analysis, combining signals from arrays of seismometers to estimate directionality. Results begin pointing tentatively toward the North Atlantic, particularly near the continental shelf off the coast of Africa. One region that draws attention is the Gulf of Guinea. It's an area where ocean swells from different directions can intersect, and where the seafloor geometry might amplify pressure oscillations. You picture waves converging over a broad continental shelf. Energy focuses downward. The crust flexes slightly. That flexing sends seismic waves radiating outward, wrapping around the globe. Every 26 seconds, another cycle. It's elegant, almost disappointingly elegant. No alien transmitters, no subterranean supermachines. Just wind, water, and rock in intricate conversation. But the elegance hides complexity. Ocean conditions are wildly variable. Storm intensity fluctuates. Wave spectra shift. If the 26-second signal were purely storm-driven, you might expect more irregularity. Yet the pulse maintains a striking steadiness over long timescales. The open scholarly debate sharpens once more. Historians still argue whether the observed stability arises from averaging effects across multiple storm systems worldwide, or whether a specific geographic sweet spot consistently reinforces the same frequency. In other words, is the planet being played by a chorus of storms or by a particularly reliable soloist? You let your thoughts sink beneath the waves now, down past the sunlit surface into darker water, where pressure increases and light fades. At the seafloor, sediment layers blanket older rock. When wave-induced pressure variations reach this boundary, they don't cause dramatic cracking. They cause tiny elastic flexing. The crust bends ever so slightly, then rebounds. Over and over. The movements are microscopic. You would never feel them standing on a beach. But seismometers do. And here's the quietly astonishing part. These ocean-driven microseisms can propagate thousands of kilometers inland. Even landlocked regions can hear the ocean storms through the ground. The planet is acoustically connected in ways that feel almost poetic. You imagine lying in the middle of a continent, far from any shoreline, and still being subtly vibrated by distant waves. It's like feeling the best from a party happening miles away. Except the party is a North Atlantic storm system, and the dance floor is the Earth's crust. Is there something soothing in that interconnectedness? Surface weather influencing deep vibrations? Energy transferring across boundaries we often consider separate. And yet, questions remain. Why 26 seconds so persistently? Why that frequency standing out so cleanly? Why does it sometimes appear stronger in specific regions? The ocean explanation grows stronger with each dataset, but it hasn't closed the case entirely. There's still room for nuance, for structural resonance effects, for mantle coupling, for complex feedback between surface forcing and deep response. You return to solid ground in your imagination. Beneath your feet, the crust feels firm, reliable. But somewhere far away, waves are colliding. Pressure pulses are pressing into rock, and every 26 seconds, the Earth answers. Not loudly, not violently, just with a quiet, persistent murmur that has been there all along, waiting for us to listen closely enough to notice. If the ocean is the drummer, then the mantle is the cathedral. You sink beneath the crust again, past the brittle shell where earthquakes crack and faults grind, and into the mantle, a realm so vast it makes the crust feel like the peel of an apple. Nearly 2,900 kilometers thick, the mantle accounts for about 84% of Earth's volume. It is solid rock, yes, but under immense pressure and temperature, it behaves less like concrete and more like an unimaginably slow river. Mainstream geology tells you that mantle convection drives plate tectonics. Heat from radioactive decay and leftover energy from Earth's formation rises in great looping currents. Hot material ascends, cooler material sinks. Over millions of years, Sunra, these currents shuffle continents across the globe. The Himalayas exist because of this creeping motion. The Atlantic Ocean widens because of it. The ground you stand on is riding a conveyor belt that moves about as fast as your fingernails grow, which is comforting because you don't need to fasten a seatbelt to go to sleep. Now imagine vibrations entering this immense layer. When ocean waves press on the seafloor, the crust flexes. That flexing launches seismic waves downward and outward. Some travel along the surface. Others dive into the mantle, refracting and reflecting as they pass through regions of varying density and elasticity. The mantle is not uniform. It contains transition zones around 410 and 660 kilometers deep, where minerals change structure under pressure. These boundaries influence how waves propagate, bending their paths like lenses in a giant rocky telescope. You picture the 26-second pulse not as a flat ripple, but as a three-dimensional oscillation weaving through this layered interior. Each cycle sends energy downward, where it interacts with mineral structures that have been under crushing pressure for billions of years. Here's where resonance becomes more intriguing. Earth's free oscillations, those global ringing modes discovered after massive earthquakes, depend heavily on mantle properties. The speed at which seismic waves travel through the mantle determines which frequencies are amplified. If ocean-driven pressure variations consistently excite a mode near 26 seconds, it implies something fundamental about the mantle's elasticity and density distribution. Historians still argue whether the 26-second signal offers a subtle window into mantle structure itself, potentially refining models of Earth's interior. It's one thing to measure mantle properties after a giant earthquake. It's another to observe a continuous, low-level excitation that might provide ongoing calibration. You imagine scientists comparing observed frequencies with theoretical models, adjusting parameters, density here, elasticity there, until predictions match reality. It's like tuning a massive, invisible instrument. A quirky tidbit slips in from the fringes of speculation. Some early enthusiasts wondered if deep mantle plumes, columns of hot material rising from near the core mantle boundary, might pulsate rhythmically. Mantle plumes are real. They are thought to feed hotspots like Hawaii and Iceland. But the idea of them beating like hearts every 26 seconds stretches physics beyond its comfort zone. Plumes move on geological timescales and not human breath intervals. If one pulsed that fast, volcanoes would resemble malfunctioning soda fountains. Still, the fact that such ideas surfaced highlights how little we directly observe of the mantle. We infer its behavior from waves, chemistry, and high-pressure experiments. No human has ever drilled more than about 12 kilometers into the crust, a record set by the Kola super deep borehole in Russia. That's barely a scratch compared to the mantle's depth. The rest is detective work. As the 26-second pulse travels through this hidden world, it experiences attenuation, gradual loss of energy due to internal friction. Yet it remains detectable across continents. That persistence suggests efficient coupling between surface forcing and deep response. The planet is surprisingly good at transmitting low-frequency energy. You let that sink in. The Earth is not just solid, it is elastic. It bends, rebounds, oscillates. The ground beneath your bed flexes by microscopic amounts constantly, even if you feel nothing. If you had seismic vision, you'd see a faint shimmer passing through everything around you. The open scholarly debate shifts slightly here. Historians still argue whether the mantle acts merely as a passive medium transmitting ocean-generated waves, or whether it actively shapes and amplifies the 26-second mode through structural resonance. In simpler terms, is the mantle just carrying the tune or harmonizing with it? That distinction is subtle but profound. A passive medium transmits. A resonant structure participates. You imagine the mantle as a vast chamber carved from rock, its mineral grains aligned under pressure, its temperature gradients sculpting wave speeds. When energy arrives at the right frequency, perhaps certain layers flex more readily, reinforcing the cycle. Meanwhile, above, storms continue their choreography. Winds sweep across the Atlantic. Swells collide. Pressure pulses descend. The surface seems chaotic, but the response below may be governed by clean mathematical relationships, equations describing wave propagation through spherical shells. There's something deeply calming about that contrast. Chaos at the surface, order in the depths, and yet mysteries remain. The 26-second pulse does not always point cleanly to one location. Its directionality shifts subtly with seasons. That variability suggests the mantle's role is not static. Different source regions may excite the same mode at different times, like multiple pianists pressing the same key from opposite sides of the stage. You drift even deeper in your imagination, toward the core mantle boundary nearly 2,900 kilometers down. Temperatures there rival the surface of the sun. Pressures exceed 1,000,000 times atmospheric levels. The mantle meets the liquid outer core, a swirling ocean of molten iron and nickel responsible for Earth's magnetic field. Could vibrations from above reach this boundary? In theory, yes. Low-frequency waves can penetrate deeply. Whether the 26-second mode significantly interacts with the core is still uncertain, but the possibility adds another layer of intrigue. For now, though, the evidence leans toward a surface-driven process coupled with mantle resonance. Ocean storms provide energy, the crust flexes, the mantle transmits and possibly amplifies. Every 26 seconds, the cycle completes. You rest with that rhythm. Imagine it passing beneath mountains, deserts, cities. Imagine it threading through mineral structures forged billions of years ago, long before animals walked on land. The planet is not silent stone. It is a layered instrument, gently played by wind and water. And somewhere within that immense cathedral of rock, the 26-second note continues to hum, steady, patient, and quietly revealing that even the deepest parts of Earth are connected to the restless sea above. If the mantle is the cathedral, then the core is the furnace at its center. Unless you drift downward to the boundary nearly 2,900 kilometers beneath your feet, where solid silicate rock gives way to liquid metal. The outer core is a vast ocean of molten iron and nickel, swirling at temperatures comparable to the surface of the sun. It is this churning metallic layer that generates Earth's magnetic field through a process called the geodynamo. Without it, compass needles would spin uselessly, solar radiation would strip at the atmosphere more aggressively, and life as you know it would look very different. So yes, you can thank a spinning ball of liquid metal for not being constantly microwaved from space. Mainstream geophysics established the existence of the liquid outer core in 1936, when Danish seismologist Inge Lehmann analyzed earthquake wave behavior and deduced that Earth must contain a solid inner core surrounded by liquid. She noticed that certain seismic waves behaved in ways only explainable if a distinct inner boundary existed. It was a quiet revolution, one that reshaped how we imagine the planet's deepest interior. So naturally, when confronted with a persistent global vibration, some scientists asked, could the core be involved? You imagine the outer core as a slow metallic storm system. Convection currents swirl as heat escapes from the inner core. These motions generate electrical currents, which in turn create magnetic fields. The entire system is dynamic, chaotic, and immense. If anything inside Earth were capable of rhythmic motion, surely this molten ocean could. But there's a problem. Core dynamics operate on timescales far longer than 26 seconds. Magnetic field variations unfold over years to centuries. Even fluid motions inside the outer core, while vigorous on geological scales, do not pulse neatly every half minute. If the core were beating at 26-second intervals, compasses around the world might start jittering like nervous squirrels. They do not. Still, the possibility isn't dismissed immediately. Low-frequency seismic waves can travel through the mantle and reflect off the core mantle boundary. Some can even pass through the liquid outer core, though S waves cannot propagate in liquid. The behavior of P waves and other complex modes allows scientists to probe these depths indirectly. The question becomes, is the 26-second signal interacting with the core in a measurable way? Historians still argue whether early modeling efforts sufficiently accounted for subtle core-mantle coupling effects when interpreting the pulse. The boundary between mantle and core is not smooth. It contains irregular structures, ultra-low velocity zones, and chemically distinct patches that may influence how waves scatter and resonate. You imagine vibrations descending from ocean-driven flexing, traveling through the mantle, and encountering this turbulent metallic sea. Some energy reflects upward, some refracts. Perhaps a faint echo returns, reinforcing the oscillation. It's an elegant thought, but current evidence suggests the core is not the primary driver. A quirky fringe idea once floated through speculative circles. What if fluctuations in the geodynamo itself created periodic mechanical vibrations detectable at the surface? And the image is cinematic. Earth's magnetic engine thumping like a colossal piston. But magnetic field variations are measured in nanoteslas over years, not in mechanical pulses every 26 seconds. Physics gently but firmly escorts that theory out the door. Still, exploring it sharpens the investigation, because eliminating the core narrows the field. If the pulse is not generated deep within the metallic heart, then it is likely excited higher up, by processes closer to the surface that couple efficiently with the planet's resonant modes. You let your attention hover at the core mantle boundary. This region, known as the D prime layer, is one of the most mysterious zones inside Earth. Seismic studies reveal complex structures here, patches where waves slow dramatically, suggesting partial melting or unusual compositions. Some researchers propose that remnants of ancient subducted plates accumulate in this region, forming piles of colder material. Others suggest chemical interactions between core and mantle create exotic mineral phases. The open scholarly debate resurfaces. Historians still argue whether subtle structural heterogeneities at the core-mantle boundary could preferentially amplify certain global oscillation modes, including one near 26 seconds. In other words, even if the core isn't the drummer, could it be shaping the acoustics? You imagine a grand instrument whose deepest chamber alters the tone produced by surface vibrations. The energy originates in storms and waves, but the final sound depends on the instrument's full architecture, from crust to core. And yet, models indicate that the dominant energy source remains surface-driven microseisms. The 26-second pulse aligns more closely with known ocean wave interactions than with any intrinsic core oscillation. There's something almost reassuring about that, because while the idea of Earth's molten heart thumping unpredictably might sound dramatic, a storm-driven resonance feels grounded. Literally, wind moves water, water presses rock, rock vibrates, physics behaves. Still, you can't help but appreciate the interconnectedness. Even if the core isn't setting the rhythm, it exists within the same vibrational system. Every oscillation passing through the mantle brushes the core mantle boundary. Every pulse subtly reminds you that Earth is layered but unified. You rise slightly in your mental descent and back into the mantle where the 26-second mode likely finds its sweet spot. The core recedes into glowing darkness below, less a metronome and more a silent partner in the planet's structural symphony. And above, storms continue their restless choreography. The investigation has now ruled out classic earthquakes. It has dismissed human industry. It has considered and largely set aside the molten core as a primary source. What remains is a picture of coupling, ocean energy exciting a natural resonance in the solid Earth. But one question lingers softly in the background. If the North Atlantic plays such a significant role, could specific geographic features, continental shelves, underwater ridges, coastal geometries, be acting as amplifiers? You let that curiosity settle like a slow breath, because somewhere along the edge of a continent, ash waves are colliding, pressure pulses are descending, and every 26 seconds the planet responds, not from its fiery heart, but from the vast, elastic body wrapped around it. The furnace burns steadily below. The rhythm, however, belongs to wind and water. You drift back upward now, not all the way to the surface, but to the edges of continents where land, sea, and deep time meet in complicated geometry. For a while, the North Atlantic held most of the spotlight. Storms, swells, continental shelves, it all fit neatly. But as researchers refined their beamforming analyses, triangulating subtle directionality from seismic arrays, another region began to glow faintly on the map: West Africa, the Gulf of Guinea. It's not the first place your imagination jumps when you think of planetary mysteries. No dramatic volcano chain like the Pacific Ring of Fire. No famous fault line like California's San Andreas. Just a broad sweep of coastline curving gently into the Atlantic, with a wide continental shelf beneath shallow water. And yet sometimes it's the quiet geography that matters most. Here's the mainstream geological fact anchoring this shift. Continental shelves can significantly amplify ocean wave pressure signals because shallow water allows wave energy to interact more strongly with the seafloor. When long-period swells move over broad shelves, the pressure variations at the bottom can become especially coherent. In certain configurations, opposing wave systems can interfere in ways that generate strong, rhythmic microseisms. The Gulf of Guinea has precisely such a configuration: wide shelf, complex bathymetry, and exposure to Atlantic swells arriving from multiple directions. You imagine long ocean swells rolling in from distant storms, colliding with reflected waves from the African coastline. Their interaction produces pressure oscillations that press down on the seafloor every 26 seconds. The crust flexes. Energy radiates outward as seismic waves, wrapping around the globe like invisible ripples in a planetary pond. It's less cinematic than a molten core heartbeat, but in science, elegance often beats drama. Historians still argue whether early focus on the North Atlantic delayed recognition of the Gulf of Guinea's potential role. Data coverage in parts of Africa was historically sparser than in North America and Europe. Seismic stations were fewer, oceanographic measurements were limited. Sometimes mysteries persist simply because you're not looking in the right place with the right tools. As instrumentation improved and global collaboration expanded, the picture sharpened. You picture scientists overlaying seismic back projection maps with ocean wave models. Colored arrows converge along the West African margin. The 26-second energy seems to bloom strongest there during certain seasons. It's not exclusive. Other regions contribute, but this area stands out like a subtle hotspot. A quirky tidbit makes its quiet entrance. Local folklore along parts of the West African coast sometimes speaks of the ocean as having moods and breaths, as if it inhales and exhales with intention. Of course, folklore isn't seismic data, but there's something poetic about the idea that coastal communities long sensed rhythms modern instruments are only now quantifying. Back in the lab, the physics becomes clearer. When two wave trains of similar period travel in opposite directions, they can create what's known as a standing wave pattern in the ocean. That pattern doubles the frequency of the original waves in the pressure signal at the seafloor. If dominant swells in the region hover around 13 seconds, their interaction naturally produces a 26-second microseism. Suddenly, the number that felt mysterious begins to look mathematically inevitable. You almost want to apologize to the planet for suspecting alien transmitters. Still, the signal's global coherence remains impressive. From a relatively localized stretch of continental shelf, an energy spreads through Earth's elastic body and becomes detectable worldwide. That tells you something profound about wave propagation in spherical solids. Low-frequency seismic waves attenuate slowly. They travel far. They curve along great circle paths. They overlap and interfere. The open scholarly debate refines itself. Historians still argue whether the Gulf of Guinea is the dominant persistent source of the 26-second signal, or merely one of several reinforcing regions that collectively sustain the mode year-round. Ocean systems are interconnected. Swells born near Antarctica can traverse entire basins. The Southern Ocean, with its famously uninterrupted roaring 40s winds, may also contribute energy under the right conditions. You let your thoughts circle Antarctica briefly. Vast ice sheets, relentless winds, enormous waves wrapping around the continent. It's tempting to imagine icy coastlines acting like giant resonant edges. Some studies have indeed suggested Southern Ocean contributions to long-period microseisms, but for the specific 26-second peak, West Africa continues to stand out prominently in many analyses. And there's something calming about narrowing the source. Instead of a vague planetary enigma, you now have a place, a stretch of coastline, a shelf beneath shallow Atlantic water, storm-driven swells meeting their reflections, a natural physics experiment running continuously, day after day. You imagine standing on that coast at dusk, the air heavy with salt, waves rolling in steady rhythm. You feel nothing unusual beneath your feet, no tremor, no vibration, just the familiar hush of surf. Yet every 26 seconds, a subtle pressure cycle presses into the seabed below, sending energy into the planet. The Earth responds not because it's unstable, but because it's elastic. And elasticity is a kind of quiet resilience. It means the planet can absorb, transmit, and dissipate energy without fracturing. It means surface chaos doesn't automatically translate into catastrophe. The 26-second pulse is not a warning sign. It's not a precursor to disaster. It's the byproduct of ordinary physics playing out on a spherical stage. You feel the tension ease slightly here. The mystery hasn't vanished entirely. There are still modeling uncertainties, seasonal shifts, amplitude puzzles. But the outline of the explanation feels grounded. Wind moves water, water presses rock, rock vibrates at a natural frequency. The planet hums, not because something is wrong, but because everything is connected. And as you drift further into the story, the signal transforms from a frightening unknown into a gentle reminder. Even the deepest parts of Earth are in conversation with the restless sea. Every 26 seconds, that conversation continues, quiet, persistent, and far more ordinary than you might have feared when we first stepped barefoot onto solid ground. Once you accept that waves can press on rock hard enough to make the whole planet murmur, your imagination starts wandering toward other subterranean suspects, volcanoes. After all, if anything on Earth seems capable of rhythmic underground behavior, it's a magma chamber. You picture molten rock pooling beneath a volcano, gases bubbling, pressure building, conduits flexing like organic plumbing. It's easy to imagine some deep reservoir inhaling and exhaling every 26 seconds, like a geological yoga instructor. And to be fair, volcanoes absolutely generate seismic signals. Here's the mainstream fact. Volcanic tremor is a well-documented phenomenon. Unlike the sharp, sudden jolt of a tectonic earthquake, volcanic tremor can produce sustained, rhythmic seismic vibrations lasting minutes to days. These tremors are often linked to magma movement, gas flow, or pressure oscillations within conduits. Mount St. Helens, Kilauea, Etna, many active volcanoes have displayed harmonic tremor before or during eruptions. So the idea isn't absurd. You imagine researchers overlaying global volcano maps with seismic data from the 26-second pulse. The Pacific Ring of Fire glows with potential. Iceland straddles a mid-ocean ridge. Indonesia bristles with active cones. If a specific volcano were pulsing at a steady interval, it might produce a repeating signal. But here's the complication. Volcanic tremors are typically localized. Their seismic energy diminishes with distance. While powerful eruptions can register globally, subtle harmonic tremors usually don't create clean, persistent signals detectable across continents for years on end. And critically, volcanic tremor frequencies often vary as magma dynamics change. They are not known for clockwork precision over decades. The 26-second pulse, by contrast, has an almost metronomic consistency. Historians still argue whether early comparisons between volcanic tremor spectra and the 26-second signal were thorough enough, especially given that some deep volcanic systems remain poorly monitored. And it's true that oceanic volcanoes, particularly those far offshore, are harder to study. Submarine volcanoes can rumble without dramatic surface signs. Entire mountain chains lie hidden beneath the sea. You drift to the mid-Atlantic ridge, where tectonic plates slowly pull apart and magma rises to fill the gap. It's a restless region. Could rhythmic magma supply pulses there generate long-period oscillations? Scientists examine the frequency content carefully. Volcanic tremors often cluster in higher frequency ranges, fractions of a second to a few seconds. Long-period volcanic signals do exist, sometimes in the 10 to 30-second range, associated with fluid-filled crack resonance. But they typically fluctuate in amplitude and are geographically constrained. The 26-second microseism, in contrast, WE appears globally and correlates strongly with ocean wave activity rather than volcanic unrest. Still, the volcanic angle isn't dismissed lightly. A quirky tidbit from the early 2000s. A few curious observers speculated that an undiscovered superplume beneath Africa, where seismic imaging has revealed large low-velocity provinces deep in the mantle, might be pulsing. These massive mantle structures, sometimes called blobs, are thought to be chemically distinct regions near the core mantle boundary. They influence mantle convection and possibly surface volcanism. The image is dramatic, a continent-sized structure breathing slowly beneath Africa, sending rhythmic signals upward. But physics again gently intervenes. Mantle plumes and deep superstructures evolve over millions of years. Why their dynamics are not synchronized to half-minute cycles? If one pulsed that quickly, Earth's geology textbooks would need emergency revisions. Instead, researchers return to comparing timing. When major storms sweep the Atlantic, the 26-second signal strengthens. When seas calm, it weakens slightly. There is no comparable correlation with volcanic eruptions. Significant eruptions, like the 2010 Eyjafjallajökull event in Iceland, do not produce a lasting global 26-second rhythm. That absence is telling. You imagine seismologists examining spectrograms during volcanic crises, scanning for that familiar peak. It remains steady, unaffected by magma theatrics. The open scholarly debate shifts subtly. Historians still argue whether minor volcanic contributions might occasionally reinforce the 26-second mode regionally, even if they are not the primary driver. Earth systems rarely operate in isolation. It's possible that under certain circumstances, volcanic tremor energy overlaps with ocean-generated frequencies, briefly amplifying the signal in specific areas. But as a persistent global phenomenon, volcanoes don't fit the profile, and perhaps that's comforting, because volcanic tremor often signals unrest, rising magma, potential eruption. The 26-second pulse, however, hums through peaceful decades without heralding catastrophe. It is background, not alarm. You settle into that realization. The planet is noisy in countless ways. Faults snap, magma shifts, ice cracks, rivers erode. But the signal we're following behaves differently. It doesn't spike during eruptions. It doesn't migrate with tectonic stress changes. It doesn't crescendo before disasters. It simply continues. Every 26 seconds, wind pushes water. Water presses rock. Rock vibrates. You imagine standing on a volcanic slope at twilight, feeling nothing unusual beneath your boots. Even here, in a place defined by fire and molten stone, the deeper rhythm you're tracing comes not from magma below, but from waves thousands of kilometers away. There's something quietly profound about that. The most persistent global seismic rhythm isn't born of Earth's internal violence, but of its surface weather. Not fire, but wind. Not rupture, but resonance. And so the volcanic suspect fades into the background, not dismissed entirely, but no longer central to the mystery. The pulse remains what it has increasingly appeared to be, a conversation between ocean and solid Earth, amplified by structure, sustained by storms, and carried through mantle and crust with patient elasticity. Beneath every volcano, beneath every city, beneath wherever you happen to be listening right now. The rhythm continues, steady, unthreatening, and deeply, almost soothingly, natural. By this point, you've descended through mantle cathedrals, hovered over molten metal oceans, and stood on West African shores listening to invisible pressure pulses. The explanation feels increasingly grounded in physics: wind, water, resonance. And yet, there's always that lingering modern suspicion. What if it's us? After all, humans have become a geological force. We move mountains, sometimes literally. We blast tunnels, drill kilometers into crust, detonate explosives, construct dams that redistribute billions of tons of water. There's even a term for our seismic footprint: anthropogenic seismicity. Here's a solid mainstream fact. Underground nuclear tests during the 20th century were detected by global seismic networks, sometimes within minutes. Seismology became a critical tool for monitoring compliance with nuclear test ban treaties. Even relatively small detonations produce characteristic waveforms distinguishable from natural earthquakes. The planet keeps receipts. Mining operations, geothermal drilling, large-scale fracking, these can also generate measurable tremors. In places like Oklahoma, injection wells have been linked to increased earthquake activity over the past few decades. Human activity can and does shake the ground. So it's reasonable to ask, could a repeating 26-second pulse be the signature of some industrial process? In a massive offshore drilling platform? A deep-sea installation, cycling machinery? Some classified experiment that forgot to turn off its metronome? You imagine a secret global device humming reliably every half minute. It sounds like the plot of a late-night conspiracy documentary. Cue dramatic music. Insert blurry satellite images. Add someone whispering, they don't want you to know. But science, as always, leans on timing and distribution. The 26-second signal predates many modern offshore megaprojects. Archived data suggests it has been present in records for decades. It appears across oceans and continents, not concentrated near industrial hubs. It strengthens during storm seasons and softens during calmer periods. Hardly the behavior of a factory operating on quarterly production schedules. Hani historians still argue whether earlier seismic archives, limited in resolution, might conceal even older manifestations of the pulse. But there is no evidence of a sudden onset coinciding with a specific technological milestone. No aha moment where humanity flips a switch and the earth starts humming. Moreover, industrial vibrations tend to be localized. Even powerful machinery produces signals that decay relatively quickly with distance. For a human-made source to generate a clean, global 26-second oscillation detectable across hemispheres, it would need to inject enormous energy into the crust continuously and coherently. And if such a machine existed, it would likely be less subtle. You'd notice something. A quirky tidbit from internet lore makes a brief appearance here. Some speculative corners once suggested the signal could be linked to large-scale ionospheric heating experiments, facilities designed to study upper atmospheric physics using radio waves. The leap from radio frequency atmospheric experiments to mechanical ground vibrations every 26 seconds requires several imaginative somersaults. Fun for fiction, not for physics. Still, ruling out human causes is important. Researchers compare the pulse's amplitude against known industrial seismic signatures. They examine diurnal patterns. Does it weaken at night when industrial demand drops? It does not. They check for correlations with global shipping traffic. None compelling. They compare it to data during global slowdowns, economic recessions, and even temporary reductions in industrial activity. The 26-second rhythm persists, largely indifferent to stock markets and construction schedules. You let that settle into your thoughts. For all our impact, we are not the source of this particular murmur. There's something oddly reassuring in that. The planet's background hum is older than modern civilization. It belongs to wind systems, ocean basins, and elastic rock, not to engines and turbines. The open scholarly debate narrows further. Historians still argue whether small, localized human activities might occasionally modulate regional seismic noise at similar frequencies, but the consensus increasingly favors natural oceanic forcing as the dominant driver of the persistent global 26-second mode. In other words, even if a drilling platform somewhere happens to vibrate near that frequency, it would be a whisper layered atop a much larger natural chorus. You imagine the planet as a vast soundstage. Human activity adds percussion, short bursts, irregular taps. But the deep bass line belongs to the ocean. And here's something subtle but profound. The very ability to detect and analyze this pulse is itself a product of human ingenuity. The global seismic network, stations spread across continents, data shared internationally, is a triumph of cooperation. Scientists from different nations compare notes, refine models, argue constructively. The Earth hums and we listen together. You drift through a quiet lab at night, screens glow softly, waveforms scroll in real time. Somewhere, a storm churns over the Atlantic. Somewhere else, a coastal shelf flexes under pressure. And here, in a climate-controlled room, a thin line rises and falls every 26 seconds. Not because of secret machines, not because of hidden bunkers, but because physics is doing what physics does. Wind transfers momentum to water. Water transfers pressure to rock. Rock transfers elastic waves through the mantle. And sensitive instruments translate that into visible patterns. It's almost disappointingly reasonable. But there's beauty in that reason, because the more suspects we eliminate, earthquakes, core pulses, volcanoes, human industry, the clearer the picture becomes. The pulse is not an omen, not a glitch in the matrix, not a warning of imminent planetary upheaval. It is a steady reminder that Earth is dynamic even in calm times. And as you rest there, and comfortably far from crushing pressures and storm-tossed seas, the rhythm continues beneath you, utterly indifferent to headlines, economies, and late-night conspiracy theories. Every 26 seconds, quiet, persistent, natural. The mystery is shrinking, yes, but not disappearing. Because even when you understand the broad mechanism, subtle questions remain about resonance, amplification, and the planet's precise structural tuning. And that's where the story gently turns next, not toward fear, but toward history. Because this isn't the first time Earth has hummed in ways we didn't immediately understand. Once you realize the 26-second pulse is likely part of a broader natural hum, your attention shifts backward in time. Because here's the humbling truth. The Earth was vibrating long before anyone thought to measure it. If you imagine a seismologist in the early 20th century, hunched over smoked paper drums, where needles scratched delicate lines as the ground moved. Early seismographs were mechanical, heavy masses suspended on springs, tracing motion onto rotating cylinders. They were designed to catch earthquakes, not whispers. If a signal was too subtle, it simply blended into the background ink, and that background was often ignored. Here's a mainstream historical anchor. In 1998, researchers reported the discovery of the Earth's hum, continuous, low-frequency oscillations of the planet, even in the absence of earthquakes. Before that, most scientists assumed significant global oscillations only followed major quakes. The idea that the Earth was constantly ringing, faintly, challenged assumptions. It turned out the planet never truly stops vibrating. Historians still argue whether hints of this hum were present in much older data, but dismissed as noise. After all, when you build instruments to detect dramatic events, you don't always pay attention to the quiet in between. So researchers began digging into archived seismic records, scanning decades of continuous data for the 26-second signature. With modern computational tools, they can process enormous datasets quickly, filtering, stacking, and amplifying faint periodic signals. You picture rows of digital waveforms being aligned and averaged, tiny peaks reinforcing one another until a clean spectral line emerges around 0.038 Hz. There it is again, steady, persistent, present not just in recent years, but stretching back through older archives wherever continuous broadband data exists. The realization shifts the emotional tone of the mystery. This isn't something new. It isn't escalating. It's been there all along. A quirky tidbit surfaces from early hum research. When scientists first confirmed continuous free oscillations, some jokingly suggested that Earth was singing to itself. The phrase stuck in popular science writing, even if professionals prefer less poetic language. Still, it captures the essence. The planet doesn't require catastrophe to produce sound. It hums simply because energy is constantly moving through its systems. You let your mind wander even further back. Before seismometers, before modern science, ancient civilizations experienced earthquakes, of course. They felt the violent jolts, but they had no way of perceiving the subtle, rhythmic background oscillations beneath their temples and villages. For them, Earth was either still or shaking. There was no middle state of gentle, continuous vibration, and yet the hum was there. The open, scholarly debate refines again. Historians still argue whether improved sensor sensitivity in the late 20th century was the decisive factor in recognizing continuous oscillations, or whether conceptual blind spots delayed their discovery. Sometimes you don't see a phenomenon because you don't think to look for it. That idea feels universal. How many subtle patterns exist around you right now, unnoticed simply because you lack the tools or the expectation to detect them? As computational power increased in the 1990s and 2000s, researchers began analyzing seismic noise, not as nuisance but as data. And noise correlation techniques allowed them to extract meaningful signals from seemingly random vibrations. By cross-correlating background noise between stations, scientists could even image subsurface structures without relying on earthquakes at all. It was a methodological revolution. The 26-second pulse benefited from this shift. What once might have been dismissed as low-frequency clutter became a feature worth investigating. You imagine the first time someone plotted a long-term spectral analysis and noticed that small but stubborn peak. Maybe they leaned closer to the screen. Maybe they thought it was a processing artifact. Maybe they reran the code. Scientists are trained skeptics. Patterns must survive doubt. And this one did. Interestingly, in archived data suggests that the amplitude of the 26-second signal fluctuates with climate patterns. Stronger during certain storm seasons, weaker during calmer years. That reinforces the oceanic link. But it also means that long-term climate variability could subtly influence Earth's background hum. You feel a quiet awe at that connection. Atmospheric circulation patterns, driven by solar heating and modulated by ocean temperatures, shape storm intensity. Storms shape wave energy. Wave energy shapes microseisms. Microseisms excite planetary resonance. The chain stretches from sunlight to seismic sensors. It's intricate, interconnected, elegant, and it reframes the initial fear that something strange and ominous was happening right now. In truth, the signal has been humming through world wars, industrial revolutions, ice ages, and quiet centuries alike. The Earth's murmur is not new. We are new listeners. You settle into that perspective. When something is first detected, it can feel urgent, like a sudden anomaly demanding explanation. But often, discovery is less about change in the world and more about change in perception. The planet didn't suddenly start pulsing at 26-second intervals. We simply developed the patience and sensitivity to notice. There's comfort in that realization. The signal is not an alarm. It is not escalating. It is part of the baseline symphony of a dynamic planet. Still, even with historical data in hand, questions linger. Why is that specific frequency so prominent? How precisely does ocean wave interaction lock into Earth's structural modes? Could subtle long-term changes in storm patterns alter the hum's character? An understanding deepens, but curiosity remains. And as you rest there, aware now that the ground beneath you has likely been vibrating gently your entire life, you begin to appreciate the shift in mindset. What once seemed like a mysterious intrusion now feels like a long-standing companion. Every 26 seconds, the planet completes another quiet cycle, not because something is wrong, but because Earth, in all its layered complexity, has always been in motion, even when we weren't listening. Now that you know the hum has been there all along, your attention settles on a deeper question. Not where the energy comes from, but why that specific note carries so clearly through the planetary symphony. You return to resonance. In 1954, after the Great Alaska Earthquake, scientists confirmed that Earth can oscillate in discrete normal modes, specific frequencies determined by its size, density, and internal structure. When excited strongly enough, the entire planet vibrates in patterns that can be mathematically described, almost like spherical harmonics drawn across a globe. Some modes involve the whole Earth expanding and contracting slightly. Others involve more complex nodal patterns, where certain regions move, while others remain relatively still. This is not poetic exaggeration. After the 2004 Sumatra-Andaman earthquake, instruments detected Earth ringing for days in multiple modes. The planet behaved like a struck bell. That's mainstream, textbook geophysics. But what fascinates you now is that these modes don't require catastrophe to exist. They are always available, like keys on a piano waiting to be pressed. The 26-second pulse appears to align closely with one of Earth's spheroidal normal modes. Not the loudest, not the most dramatic, but one that the planet seems particularly willing to sustain when nudged gently and repeatedly by ocean wave forcing. You imagine the Earth as a vast, layered instrument. The crust forms the outer shell. The mantle provides bulk and elasticity. The core adds mass and boundary conditions. Each layer shapes the tonal qualities of the whole. When storms over the Atlantic generate pressure oscillations at just the right interval, they don't create a new sound. They excite an existing one. Historians still argue whether the 26-second signal is best understood as a continuously driven normal mode or as a quasi-resonant amplification of microseismic noise near that frequency. The distinction is subtle but meaningful. In one case, you have a clean global oscillation sustained by external forcing. In the other, you have a statistical peak emerging from overlapping noise sources. Either way, the physics converges on the same comforting conclusion. The planet is behaving exactly as a large elastic sphere should. You picture a globe suspended in darkness. Invisible waves ripple through it, reflecting and refracting at internal boundaries. Every 26 seconds, a global pattern briefly strengthens, slightly compressing and relaxing regions by microscopic amounts. You would never feel it. The displacement is measured in nanometers. If you tried to detect it with your body, you'd fail spectacularly. Good thing you're not a seismometer. A quirky tidbit makes you smile. Some early researchers joked that if humans were as sensitive as broadband seismic sensors, we'd never sleep. The Earth's constant vibrations would feel like lying on a gently humming engine. Thankfully, our sensory systems filter out such subtlety. Evolution did not design us for nanometer awareness. Still, the idea that the entire planet is flexing ever so slightly every half minute has a strangely meditative quality. The open scholarly debate continues in modeling circles. Historians still argue whether long-term changes in ocean circulation patterns, perhaps linked to multi-decadal climate oscillations, could subtly shift the amplitude or even the exact period of this resonance. If storm tracks migrate or wave energy distributions change, the forcing might evolve. That doesn't mean disaster. It simply means the hum is part of a living system. You let your thoughts trace the chain again. Solar radiation warms equatorial oceans. Temperature gradients drive atmospheric circulation. Winds generate waves. Wave interactions produce pressure oscillations. Pressure oscillations flex the seafloor. Elastic waves propagate through crust and mantle. A normal mode resonates faintly at 26 seconds. From sunlight to seismic hum. It's almost absurdly elegant. And there's something deeply reassuring about resonance. Resonant systems are predictable. They follow equations. They don't imply instability. They imply structure. The fact that Earth has preferred vibrational modes tells you it is coherent, not chaotic. Of course, while coherence doesn't mean simplicity, the mantle's mineral composition affects wave speed. The transition zone near 660 kilometers depth introduces subtle reflections. The core mantle boundary shapes energy partitioning. Each layer tweaks the final tone. Researchers refine their models constantly, using the hum as an additional calibration tool. In fact, continuous background oscillations are now used in a field called ambient noise tomography. By analyzing persistent seismic noise between stations, scientists can image subsurface structures without waiting for earthquakes. The hum becomes a flashlight in the dark interior. You find that delightful. What was once dismissed as noise is now signal. What seemed like interference is information. And so the 26-second pulse is no longer just a curiosity. It's a diagnostic tool, a steady probe revealing properties of the deep Earth. Every cycle carries structural data encoded in wave speed and attenuation. You imagine Earth as both instrument and teacher. Tap it gently with ocean waves and it answers. Listen carefully and you learn about its layers. The fear that something strange is happening dissolves further here. The signal isn't an anomaly in the sense of being unnatural. It's an emergent property of a dynamic system operating under well-understood physical laws. And yet, its existence still inspires wonder. Because even though the explanation is grounded, the scale is staggering. A storm thousands of kilometers away can excite a vibration detectable across continents. A wave crest rolling toward Africa can contribute to a global oscillation. The boundary between local weather and planetary structure is thinner than it appears. You rest in that thought. Every 26 seconds, the Earth subtly flexes, not violently, not dangerously, but faithfully, like a slow breath in a vast sleeping body. And you, lying comfortably far from mantle convection and ocean swells, are carried along by a rhythm you never knew was there. Not because it just began, but because you finally tuned in to the quiet music of a planet that never truly stops moving. Now that you understand the hum as resonance, wind and water nudging a willing planet, you begin to notice something subtler. The amplitude isn't perfectly constant. Some years, the 26-second peak appears slightly stronger in global datasets. Other years, it softens. Not dramatically. Not in a way that would wake you at night, but enough for careful analysts to raise an eyebrow over their coffee. And that gentle fluctuation leads to a modern question that floats quietly into the room. Could climate patterns influence the planet's hum? Here's a grounded mainstream fact. Ocean wave energy is directly tied to wind intensity, storm frequency, and large-scale atmospheric circulation patterns, such as the North Atlantic Oscillation, NAO. During positive NAO phases, pressure differences between the Azores and Iceland intensify, strengthening westerly winds across the North Atlantic. Stronger winds generate more energetic waves. More energetic waves produce stronger microseisms. The chain is clear. Historians still argue whether long-term climate shifts, especially those linked to anthropogenic warming, are measurably altering global microseismic energy levels. Some studies suggest that as storm tracks shift poleward or intensify, background seismic noise in certain frequency bands may increase. Others caution that variability is complex and multi-decadal, making clear attribution difficult. In other words, it's complicated, which is scientists speak for, we're still figuring it out. You imagine storm systems fueled by warmer ocean surfaces, drawing extra moisture, spinning with slightly different intensity. Waves respond accordingly. Pressure pulses at continental shelves adjust. The 26-second resonance hums just a bit louder during active seasons. Not as an alarm, not as a warning siren, but as a subtle barometer of atmospheric energy. A quirky tidbit makes you smile gently. In recent years, some researchers have even explored whether seismic noise records could serve as indirect climate proxies. Long-term archives of storminess encoded in Earth's vibration history. Imagine future scientists analyzing 21st century seismic hum to reconstruct how storm energy evolved over decades. The ground beneath us is a climate diary. There's something poetic about that. The open scholarly debate sharpens delicately here. Historians still argue whether any observed upward trends in low-frequency microseism amplitude can be confidently linked to human-driven climate change, or whether natural variability, El Niño cycles, decadal oscillations, shifting wind belts, dominates the pattern. The key point is subtlety. Even if climate influences the hum, the effect is incremental. The 26-second pulse is not suddenly doubling in strength. It's not morphing into something chaotic. It is responding proportionally to energy input, as any elastic system would. You let your breathing slow as you think about scale. Storms are loud. Headlines are loud. Climate debates are loud. But the Earth's resonant response is quiet. Every 26 seconds, a cycle completes. A faint compression, a release, a whisper of elastic memory traveling through mantle and crust. You imagine lying on a vast grassy plain under a night sky. The air is still. You cannot feel the oscillation beneath you. And yet it's there, like the faintest background note in a symphony too large for human ears. There's something deeply calming in that persistence. The planet does not overreact. It does not panic. It responds in proportion to forces applied. Wind intensifies. The hum grows slightly. Storms calm. When the hum softens, physics remains steady. A mainstream reminder grounds you again. Earth has experienced massive climate shifts before. Ice ages, greenhouse periods, abrupt warming events long before industrial civilization. Through all of it, ocean waves rolled, shelves flexed, and the planet vibrated at its natural modes. The 26-second resonance likely existed through glacial maxima and interglacial warmth alike. You feel a quiet continuity stretch backward through time. Ice sheets advancing across continents, sea levels falling, storm tracks shifting southward. Still, waves collide. Still, pressure pulses descend. Still, Earth hums. And now, in the present moment, satellites orbit overhead, measuring sea surface temperatures. Buoys bob in the Atlantic, recording wave heights. Seismometers listen from bedrock vaults around the world. Data streams converge in quiet server rooms. Every 26 seconds, another data point. The fear embedded in the phrase, "a strange signal is coming from inside the planet right now," begins to dissolve completely here. Yes, it is coming from inside the planet, but it is not born there in isolation. It is the echo of wind on water, sunlight on atmosphere, energy flowing through interconnected systems. It is Earth doing what Earth does. The pace of this realization slows your thoughts. Imagine the mantle flexing gently. Imagine the core, molten and steady. Imagine waves crossing the Atlantic tonight. Imagine a seismometer quietly tracing its thin, patient line. Nothing dramatic, nothing urgent, just continuity. The hum is not a crisis. It is not a countdown. It is not a glitch in reality. It is the soft, mechanical breathing of a dynamic world. And as you rest with that idea, you feel the story itself beginning to soften. The mystery has unfolded into understanding. The ominous unknown has transformed into elegant physics. Every 26 seconds, the cycle completes, and you, safely cradled on the crust, are part of that system. Not threatened by it, but gently carried within it. The rhythm continues, steady, unhurried, patient as the planet itself. And yet, even after physics offers its elegant explanation, the human imagination doesn't retire quietly. Because whenever you tell someone, "There's a strange repeating signal coming from inside the Earth," their eyebrows do a little synchronized dance. It sounds like the opening line of a science fiction film. The kind where someone in a dim control room whispers, "It's not random." Before ocean wave resonance took center stage, one stranger ideas briefly drifted through public conversation. Not in peer-reviewed journals, but in late-night forums, speculative blogs, and documentaries with dramatic voiceovers. You can almost hear the soundtrack. What if it's a hidden underground structure? What if it's an ancient machine? What if it's not natural? It's easy to smile at those leaps now, but they reveal something important about how humans respond to mystery. When a pattern appears, especially a rhythmic one, your brain wants agency behind it. Repetition feels intentional. Metronomes imply musicians. Here's a grounded historical fact. In 1967, astrophysicists Jocelyn Bell Burnell and Anthony Hewish detected a mysterious repeating radio signal from space. It pulsed so regularly that, for a brief moment, it was jokingly labeled LGM1 for Little Green Men. Of course, it turned out to be a pulsar, a rapidly rotating neutron star emitting beams of radiation. But that moment captures a universal instinct. When nature behaves rhythmically, we briefly suspect intelligence. The 26-second Earth signal triggered a softer version of that instinct in some corners of the public imagination. Historians still argue whether media framing sometimes amplifies mystery before evidence has time to settle. A phrase like "signal from inside the planet" carries cinematic weight. Add "right now" and suddenly it feels urgent, like the Earth is trying to text you. But science moves more patiently. A quirky fringe theory once suggested the signal might be linked to a vast undiscovered cavity deep underground, an echo chamber amplifying mechanical vibrations. The hollow Earth concept, though thoroughly debunked centuries ago, still floats around the edges of speculative culture. The problem, of course, is gravity. A hollow planet would behave very differently under orbital mechanics, and seismic wave travel times clearly show a dense interior. Earth is not an empty drum waiting to be tapped. Still, the metaphor persists because it's vivid. You imagine standing inside a colossal sphere, listening to echoes. But in reality, the Earth's interior is anything but hollow. It is layered, compressed, dense beyond ordinary intuition. Seismic waves travel through it in ways that match solid and liquid phases, not cavernous voids. Another imaginative leap tied the signal to geomagnetic phenomena, perhaps fluctuations in Earth's magnetic field coupling mechanically with the crust. It sounds sophisticated at first, but magnetic variations do not exert sufficient mechanical force on the lithosphere to create global oscillations of that clarity. The geodynamo hums in electromagnetic terms, not in rhythmic mechanical pulses every half minute. And then there were the alien probe ideas. If an advanced civilization wanted to signal humanity discreetly, why choose a 26-second seismic oscillation detectable only by specialized instruments? It's not exactly primetime broadcasting. Even interstellar engineers, one assumes, would opt for something more attention-grabbing. Still, the appeal of those ideas reveals something tender about human psychology. Mystery invites narrative. Narrative invites meaning. The open scholarly debate in this realm isn't about aliens, of course. It's about communication, how scientific uncertainty is conveyed to the public. Yes, historians still argue whether emphasizing unresolved aspects of a phenomenon can unintentionally create space for speculation that outruns evidence. In this case, the speculation faded as data accumulated. Beamforming analyses pointed toward oceanic sources. Seasonal correlations matched storm patterns. Spectral peaks aligned with known normal modes. No anomalies in magnetic data. No correlation with tectonic unrest. No escalating amplitude. The signal remained steady. Ordinary in origin, extraordinary only in scale. You feel a kind of gentle amusement at how quickly the unknown can sprout wild explanations. It's not stupidity, it's storytelling instinct. Your mind prefers a dramatic cause over a subtle chain of wind, wave, and rock elasticity. But sometimes the truth is more beautiful than the drama. The idea that sunlight heating tropical oceans can, through a cascade of physical processes, produce a detectable oscillation in the mantle of a planet thousands of kilometers thick, that's astonishing. No aliens required, and there's something calming about demystification, because fear often grows in informational gaps. When you fill those gaps with physics, measured, modeled, tested, the shadows recede. What remains isn't disappointment, it's clarity. You imagine the Earth tonight. Storm systems roll over the Atlantic. Waves intersect along the West African shelf. Pressure pulses descend. Elastic waves propagate. A spheroidal mode hums faintly at 26 seconds. Not as a coded message, not as a warning beacon, not as a planetary distress signal. Just resonance. And resonance, at its heart, is cooperation between forces and structure. When wind cooperates with water, water cooperates with rock, rock cooperates with geometry, every layer participates. The story that began with ominous phrasing, "A strange signal is coming from inside the planet right now," has transformed. Yes, the signal exists. Yes, it is inside the planet. Yes, it is happening right now. But it is not strange in the sense of unnatural. It is strange only because you had not noticed it before. And that distinction makes all the difference. The Earth is not sending a message. It is simply being itself, dynamic, elastic, interconnected. Every 26 seconds, another quiet cycle completes. And the mystery, once sharp and cinematic, has softened into something far more soothing, a steady planetary murmur that has likely been there your entire life, patiently waiting for you to listen. With mystery softened and speculation mostly settled, you turn toward the quiet technology that made all of this visible in the first place. Because without satellites, broadband seismometers, ocean buoys, fiber optic cables, and vast data archives, the 26-second pulse would still be humming unnoticed beneath your feet, like a secret too subtle for human senses. You imagine Earth from orbit. Satellites sweep overhead, mapping sea surface height to the centimeter using radar altimetry. Missions like Topex/Poseidon and its successors have, since the 1990s, measured ocean swell patterns across entire basins. They track wave energy, storm intensity, even slight bulges in sea level caused by shifting currents. From space, the ocean's surface becomes a textured map of motion. Here's a mainstream fact that grounds this beautifully. Satellite altimetry has confirmed that ocean waves can travel thousands of kilometers from their source storms, maintaining coherent energy across entire ocean basins. A storm off Newfoundland can send swells toward Europe days later. Energy is patient. It crosses boundaries. Now imagine pairing that satellite data with seismic readings from bedrock vaults on land. Researchers can correlate wave height measurements in the Gulf of Guinea with amplitude changes in the 26-second seismic peak recorded in Europe or North America. It's like watching a cause and effect chain unfold across disciplines. Oceanography shaking hands with seismology. Historians still argue whether the integration of satellite ocean data with global seismic networks in the late 20th century was the turning point in fully understanding continuous microseisms. Before satellites, wave observations were sparse. Ships, buoys, patchy coastal measurements. Now, near global coverage allows precise modeling of wave interactions over continental shelves. The pieces fit more tightly because the view widened. You picture a control room, not dramatic, just softly lit, where real-time wave models animate across screens. Color gradients show swell energy propagating toward West Africa. Beside it, a seismic spectrogram displays that familiar line at 0.038 Hz. As storms intensify, the spectral peak brightens slightly. Not alarming, not explosive, just responsive. A quirky tidbit adds a modern twist. In recent years, researchers have discovered that even undersea fiber optic communication cables, yes, the ones carrying your internet, can function as distributed seismic sensors. Using a technique called distributed acoustic sensing, DAS, tiny strain changes along the cable can detect passing vibrations. Imagine streaming a movie while the cable beneath the ocean quietly senses the planet's hum. Multitasking at a planetary level. The open scholarly debate shifts toward precision. Historians still argue how accurately we can isolate specific source regions of the 26-second signal given the complexity of overlapping wave systems worldwide. Ocean basins are rarely quiet. Multiple storms can operate simultaneously. Wave trains intersect in nonlinear ways. Untangling contributions requires increasingly sophisticated modeling. But technology keeps improving. Seismic arrays have grown denser. Ocean bottom seismometers now sit quietly on the seafloor itself, reducing the distance between source and sensor. These instruments eliminate some of the distortions introduced when waves travel long distances through heterogeneous crust. You imagine one resting in darkness beneath the Atlantic, pressure immense above it, quietly registering each 26-second flex directly from the shelf nearby. No continental detours, just a clean, mechanical whisper recorded in digital memory. And above, satellites glide silently in orbit, mapping the very storms that drive it. The interconnectedness feels almost futuristic, space technology explaining vibrations deep inside Earth. There's something comforting about the collaboration of tools. No single instrument solved the mystery. It took layers of observation, surface waves, seafloor pressure, crustal vibrations, computational modeling. And this layered approach mirrors the planet itself. Crust, mantle, core, satellite, buoy, seismometer. You settle into that symmetry. Another mainstream anchor reminds you that Earth-observing systems were originally developed for very practical reasons. Weather forecasting, navigation, disaster monitoring. Yet along the way, they revealed something quieter, the constant hum of a resonant planet. The signal that once sounded ominous now appears almost mundane in its physics, but extraordinary in its detectability. It's not loud, it's not disruptive, but it is measurable, because we built instruments patient enough to listen. Historians still argue whether future generations will uncover even subtler persistent modes hidden within seismic noise. Frequencies too faint for current networks to resolve. As sensors grow more sensitive and data analysis more refined, new peaks may emerge from the background. Perhaps there are 18-second murmurs, or 40-second whispers, or patterns shaped by distant Southern Ocean storms we haven't fully characterized. You find that thought exciting, not frightening, because each discovery doesn't signal instability, it signals refinement. The Earth isn't changing unpredictably. Your awareness is deepening. You imagine someone decades from now reviewing archived 21st century seismic data. They notice a faint but consistent modulation we overlooked. They smile, rerun models, publish quietly. Another layer of understanding added. The hum continues through it all. And right now, yes, right now, satellites are orbiting, buoys are bobbing, storms are churning, seismometers are tracing. Every 26 seconds, the cycle completes again. You can't feel it. You can't hear it. But it's there. A subtle mechanical echo of wind energy dissipating into the solid Earth. There's something almost tender about that energy transfer. Storms rage, expend their power, and part of that power becomes a faint planetary vibration instead of pure chaos. Energy disperses into structure, and structure holds. You rest in that idea. The Earth is not silent, but it is steady. Not rigid, but resilient. Not mysterious in a threatening way, but intricate in a deeply satisfying one. The strange signal is still coming from inside the planet right now. But now you know its lineage, its physics, weighing its patience. And thanks to a web of orbiting satellites and buried sensors, you are no longer listening in the dark. Now that the instruments have done their quiet detective work, you begin to notice something else. Not about the signal itself, but about the story of how humans respond to signals like this. Because this isn't the first time Earth has surprised its listeners. In the early 1900s, when Alfred Wegener proposed that continents drifted across the surface of the planet, most geologists dismissed him. The idea sounded outrageous. Continents were supposed to be fixed, rooted in place. Wegener had fossil correlations and matching coastlines, but he lacked a mechanism. It wasn't until mid-20th century seafloor mapping and seismic studies revealed mid-ocean ridges and subduction zones that plate tectonics became accepted. Historians still argue whether Wegener was rejected primarily because of insufficient evidence or because the scientific culture of the time resisted large conceptual shifts. Probably both. You let that settle. When a new pattern appears, like a 26-second pulse, it enters a scientific culture shaped by past surprises. Researchers are cautious. They remember how easily speculation can outrun data. They also remember how often noise has turned out to be meaningful. The Earth's hum itself, discovered in the late 1990s, was initially controversial. Continuous low-frequency oscillations without earthquakes? It sounded unlikely. Some suspected instrumentation artifacts. Others thought data processing quirks were to blame. Only after multiple independent teams confirmed the phenomenon did consensus emerge. The 26-second signal followed a similar arc. Less dramatic perhaps, but still illustrative. First detection, then doubt, then cross-verification, then modeling, then gradual convergence on explanation. It's almost comforting how methodical the process is. You imagine conference rooms where seismologists debate spectral peaks projected onto large screens. One researcher points out seasonal correlations. Another questions statistical robustness. A third overlays ocean wave simulations. No one shouts, "It's aliens." They argue about attenuation coefficients and boundary conditions instead. Far less cinematic, far more useful. A quirky historical tidbit drifts in here. In the 19th century, before the mechanism of earthquakes was understood, some scientists proposed that subterranean explosions of gas caused tremors. Others thought underground caverns collapsed periodically. The language of hidden chambers and internal detonations was once mainstream speculation. It took decades of seismic wave analysis to replace those images with fault rupture mechanics. In other words, Earth science has a long history of turning mystery into mathematics. The open scholarly debate today isn't about whether the 26-second pulse exists. It clearly does. It's about refinement. Historians still argue whether improvements in global station density have slightly altered amplitude estimates compared to early 2000s analyses. Are we seeing small methodological shifts or genuine variability in storm energy input? Subtle questions, nuanced answers. And nuance is the hallmark of mature science. You feel the tone of the story becoming steadier now. At first, the phrase strange signal suggested anomaly, something out of place. But history teaches you that unfamiliar does not mean unnatural. Often it simply means newly measurable. You picture the progression of tools. Mechanical drum seismographs scratching ink, analog magnetic tapes storing waveforms, digital broadband sensors sampling dozens of times per second, global data repositories streaming in real time. Each generation hears more clearly than the last. And with clarity comes humility. Because every time science resolves one mystery, it reveals deeper layers. Understanding the 26-second resonance doesn't close the book on Earth's dynamics. It opens new chapters about ocean solid coupling, climate variability, and ambient noise imaging. And you imagine future textbooks mentioning this period almost casually. Continuous microseismic excitation of Earth's normal modes, particularly near 26 seconds, is primarily attributed to ocean wave interactions along continental shelves. A neat sentence summarizing years of analysis. What once sounded ominous becomes standard curriculum. There's something deeply soothing about that trajectory. The planet doesn't become less wondrous as explanations accumulate. It becomes more coherent. Patterns interlock. Systems reveal themselves. And you, resting comfortably on the crust, are part of that unfolding understanding. The signal continues beneath you, not because it demands attention, but because energy continues to move through atmosphere and ocean. The instruments continue listening, not because they fear catastrophe, but because curiosity is endless. Historians still argue whether future generations will look back at our current uncertainties about subtle Earth processes the way we look back at early continental drift debates with affectionate bemusement. Of course, the hum correlates with multi-decadal ocean oscillations, they might say. The data were right there. Perhaps. For now, though, you sit in the present, aware of both the explanation and the humility it carries. The Earth hums, scientists listen, debate refines, understanding deepens, not in leaps of panic, but in increments of patience. And as that 26-second cycle completes again, compression, release, propagation, you feel the story's center of gravity shift fully away from fear. What remains is appreciation for elastic rock, for restless oceans, for satellites overhead, for seismometers below, for the slow, careful culture of inquiry that turns strange signals into gentle knowledge. The hum is no longer a question mark. It is a reminder that the planet is dynamic, that perception evolves, that mystery is often just a doorway waiting for better instruments. Every 26 seconds, the Earth answers a question you didn't know you were asking, and now you know how to listen. Even with all this understanding, you might still feel a faint flicker of curiosity. What don't we know? Because no scientific story ends with a neat bow. It settles into a plateau of explanation, yes, but beyond that plateau, terrain remains unexplored. The 26-second pulse is largely attributed to ocean wave interactions, exciting a natural Earth mode. That framework is solid, supported by modeling, correlated with storm data, reproduced across independent networks. And yet, historians still argue whether the exact balance between multiple source regions has been fully resolved. The Gulf of Guinea appears significant. The North Atlantic contributes strongly during winter. The Southern Ocean likely adds energy under certain conditions. But disentangling overlapping wave systems across a restless planet is not trivial. You imagine 3 storms in different basins, each sending long-period swells toward different continental shelves. Their pressure interactions overlap in time. Their seismic outputs blend. By the time the energy has wrapped around the globe, separating threads becomes mathematically delicate. It's not that we don't understand the mechanism, it's that the mechanism operates within a symphony, not a solo. Well, here's a grounded fact. Seismic wave propagation through Earth is influenced by heterogeneities, variations in temperature, composition, and structure. Even subtle mantle anomalies can alter wave speed slightly. Those small changes affect how energy from the 26-second mode distributes globally. So when researchers measure amplitude differences at distant stations, they're seeing not only source strength, but also the planet's internal architecture. In other words, the hum doubles as a probe. A quirky tidbit adds texture here. Some researchers have explored whether long-term changes in ice mass distribution, like the melting of Greenland's ice sheet, could subtly affect Earth's elastic response by altering surface loading. Large ice sheets depress the crust. Removing them allows gradual rebound. While these processes occur over years to centuries, they remind you that the planet's structure is not static even at the surface. The open, scholarly debate continues. Historians still argue whether minute shifts in Earth's rotation or angular momentum exchange between atmosphere and solid Earth have any measurable coupling to persistent low-frequency modes. The consensus so far suggests minimal direct impact at 26 seconds. But the conversation exists because Earth systems are interconnected in surprising ways. You let that complexity settle gently instead of heavily. Not knowing every decimal place does not equal ignorance. It means refinement is ongoing. There's also the question of long-term climate influence. If storm intensity distributions shift over decades, could the amplitude envelope of the 26-second hum gradually change? When early analyses hint at variability linked to known climate oscillations, but separating trend from noise requires long time series, longer than we currently possess in uniform high-resolution form. You picture researchers 50 years from now examining half a century of continuous broadband seismic data. Patterns we can't yet resolve may become obvious to them, and that's a comforting thought, because it means this story is not static. It evolves with observation. There's one more subtle uncertainty: energy dissipation. The Earth's interior absorbs and scatters vibrational energy. The rate at which low-frequency modes attenuate tells scientists about viscosity and temperature in deep mantle layers. The 26-second mode provides a continuous test signal, but extracting precise attenuation parameters remains technically challenging. And not mysterious, just intricate. You imagine the mantle not as a uniform medium, but as a tapestry of slightly warmer and cooler regions, ancient subducted slabs, rising plumes, mineral phase transitions. Each region bends waves a little differently. Each adds nuance to the hum's journey. Every 26 seconds the cycle completes, but no two cycles are perfectly identical. And that's okay. Science is rarely about absolute certainty. It's about converging lines of evidence. The 26-second pulse sits comfortably within a well-supported explanatory framework. The remaining questions are refinements, not existential threats. You breathe a little slower now. At the beginning of this journey, the phrase "strange signal from inside the planet" might have sparked unease. Now uncertainty feels gentle rather than ominous. We don't know every detail of energy partitioning across ocean basins. We don't know how multi-decadal climate variability will subtly shape amplitude envelopes. We don't know whether future sensors will reveal additional faint modes hidden beneath current resolution thresholds. But we know enough. Enough to understand the mechanism, enough to trust the physics, enough to rest easy. The Earth hums because it is elastic, because wind moves water, because water presses rock, because rock responds predictably. The unanswered questions live in the margins, in the fine print of amplitude modulation and attenuation coefficients. They are not warning signs. They are invitations for continued listening. You imagine the planet tonight. Storm systems roll across dark oceans, waves intersect along continental shelves, and pressure pulses descend into crust. Seismic waves travel outward, instruments record, researchers analyze, debates refine, and every 26 seconds, another quiet oscillation completes, slightly different in amplitude perhaps, slightly refracted by mantle heterogeneity, but fundamentally stable. What don't we know? Plenty. What do we know? Enough to understand that this signal is not a countdown, not a crack forming in the planet's heart, not an alarm hidden beneath your bed. It is a steady murmur in a living, dynamic system, and the unknowns that remain are the soft edges of curiosity, not the sharp edges of fear. The hum continues, patient, elastic, untroubled. And so do you. Now imagine the future listeners, because the Earth will keep humming long after tonight's storms dissolve, yet long after this particular winter's swells flatten into calmer seas, and the network of ears pressed gently against the crust is only growing more sensitive. You picture a new generation of seismic stations, smaller, more numerous, more affordable, quietly expanding into regions that once had sparse coverage. Parts of Africa, South America, remote islands, ocean floors. Every added station sharpens resolution. Every new data set reduces uncertainty. Here's a grounded, mainstream fact. Over the past 2 decades, the number of broadband seismic stations worldwide has increased dramatically thanks to international collaborations and open data initiatives. Networks like IRIS and other global partnerships have made continuous seismic data freely accessible to researchers everywhere. That openness accelerates discovery. The 26-second hum benefits from this density. With more stations, scientists can perform more precise beamforming, essentially steering virtual listening arrays towards suspected source regions. They can isolate seasonal variations with greater confidence. They can compare amplitude changes across hemispheres simultaneously. And then there's the ocean floor itself. Ocean bottom seismometers, once rare and expensive deployments, are becoming more common. These instruments sit directly on the seabed, closer to the action where wave pressure interacts with continental shelves. By reducing the distance between source and sensor, they help clarify how energy transfers from water to rock. You imagine one resting beneath the Gulf of Guinea tonight. Darkness absolute, pressure immense. Above it, waves intersect. Every 26 seconds, when the seabed flexes ever so slightly, the instrument records faithfully, unaware of the story it's helping to tell. A quirky technological twist enters here. Distributed acoustic sensing along fiber optic cables is beginning to turn entire stretches of undersea infrastructure into vibration detectors. Instead of a single sensor at one point, researchers can measure strain continuously along tens of kilometers of cable. It's like turning the internet's backbone into a planetary stethoscope. Historians still argue whether this proliferation of sensing technologies will reveal previously undetected persistent modes in adjacent frequency bands. As sensitivity improves, what once appeared as background noise may resolve into distinct peaks. The 26-second signal might eventually be joined by siblings, subtle oscillations we haven't yet teased out. Watch you feel excitement rather than anxiety at that possibility. Because more detail does not mean more danger. It means finer understanding. There's also a growing integration between disciplines. Oceanographers refine wave models with higher resolution wind data. Climate scientists simulate future storm track scenarios. Seismologists feed those models into elastic Earth simulations to predict how micro-seismic energy might respond. It's a web of collaboration, and through it all, the hum remains steady. Not changing character dramatically, just revealing nuance as tools improve. You imagine a control center decades from now. Artificial intelligence algorithms continuously analyze global seismic noise in real time, detecting subtle shifts in amplitude distributions across frequency bands. And not because someone fears catastrophe, but because continuous monitoring is simply standard practice. The Earth becomes not a mystery to decode in panic, but a system to observe in calm curiosity. The open scholarly debate evolves into something gentler. Historians still argue how best to quantify long-term trends in microseismic energy, given natural variability and evolving instrumentation. When sensors improve, recorded amplitudes can appear to change even if the source remains constant. Distinguishing true geophysical change from observational artifacts becomes part of the craft. It's a reminder that listening is never passive. It requires calibration, context, patience. You let your imagination zoom out. Satellites orbiting above, buoys floating at sea, fiber cables humming with data, seismometers anchored in bedrock. Researchers collaborating across time zones, all quietly attentive to a planet that never fully rests. And beneath all of it, every 26 seconds, a faint oscillation completes. Elastic, predictable, unthreatening. You notice how different the phrase feels now. A strange signal is coming from inside the planet right now. Yes, it is. But it's no longer strange in the unsettling sense. It's strange only in the sense that you had not tuned in before. You feel grounded. Because this signal doesn't spike. It doesn't escalate. It doesn't foreshadow rupture. It hums. And future listeners will hum along, mapping, refining, modeling, not out of fear, but out of wonder. There's something deeply soothing about the continuity of that effort. Long after headlines change, storms shift, and technologies upgrade, the fundamental physics remains the same. Wind will move water. Water will press rock. Rock will flex. Waves will travel. Resonance will respond. And somewhere, in a quiet lab or an ocean floor vault, an instrument will trace that thin, repeating line. Every 26 seconds. Not as a warning, not as a mystery, but as a steady reminder that the planet is alive with motion, even when it feels perfectly still beneath your feet. Now, just for a moment, let your imagination wander back to that flicker of unease you might have felt at the beginning, a strange signal from inside the planet. Right now, what if it grew stronger? It's a natural question. Whenever you hear about something rhythmic and planetary, your mind quietly checks for escalation. Is it building? Is it accelerating? Is this the prelude to something cinematic and inconvenient? Or so let's walk gently through that thought experiment. not dramatically but calmly. First, a grounding fact. The amplitude of the 26-second microseism is tiny. We're talking nanometers of ground displacement, billionths of a meter. If your mattress shifts more than that when you roll over, and it does, you are generating a larger local vibration than this global hum. So even if storm intensity increased significantly in a given season, the resulting amplification of the 26-second mode would remain extremely small relative to anything structurally dangerous. It would not crack foundations. It would not destabilize tectonic plates. It would not build up pressure in the way earthquakes do. That's because this signal is not stored stress. It's transient elastic motion. Elastic systems return to equilibrium. That's their defining trait. Historians still argue whether the language used in popular descriptions of geophysical phenomena sometimes unintentionally conflates resonance with instability. Resonance sounds dramatic, but in this context, it's simply efficient energy transfer, not runaway amplification. You imagine a child on a swing. If you push gently in rhythm, the swing moves smoothly. But if you stop pushing, friction slows it down. The 26-second mode is like that swing. The ocean pushes steadily. When storms weaken, the motion softens. There is no hidden reservoir of accumulating oscillation waiting to explode. A quirky comparison helps anchor this. Large bridges are engineered to avoid resonant amplification at frequencies induced by wind or traffic. Engineers design damping systems to prevent runaway oscillations. The Earth, however, it is not a narrow suspension bridge. It's a 12,742-kilometer wide sphere with immense mass and internal damping. Its natural modes are stable and self-limiting. Even if a once-in-a-century superstorm dumped extraordinary energy into the Atlantic, the planet's elastic response would scale proportionally and then dissipate. You let that settle like a reassuring hand on your shoulder. There is no scenario in which the 26-second hum suddenly becomes a catastrophic planetary vibration. That's not how the physics works. The open scholarly debate here is subtle and technical. Historians still argue how extreme climate scenarios might alter the statistical distribution of microseismic amplitudes over long-time horizons. Would a warmer world with more energetic storms slightly elevate average background noise levels? Possibly. But elevated noise is not structural danger. It's just slightly stronger elastic flexing. You imagine a future winter with particularly intense Atlantic storms. Wave heights surge. The continental shelf off West Africa flexes a bit more. Seismic spectrograms show a brighter line at 0.038 Hertz for a few weeks. And then the season passes. The line dims. The cycle continues. There's something deeply calming about that proportionality. Nature scales smoothly. It doesn't flip switches from whisper to apocalypse. And consider this. Earth experiences far larger vibrational events regularly, major earthquakes ringing the planet for days. Compared to those, the 26-second hum is a background murmur. If Earth were a concert hall, earthquakes are the thunderous percussion. The hum is the air conditioning system quietly doing its job. But you feel the tension drain fully now. The signal is not growing ominously. It is not evolving unpredictably. It is not a countdown to tectonic drama. It is responsive to weather, elastic in nature, damped by physics. Even if monitoring technology improves and we detect slight variations more clearly, the underlying mechanism remains steady. Wind energy in, elastic vibration out, energy dissipated as heat and scattered waves. Nothing accumulates. Nothing destabilizes. And perhaps that's the final reframing. When you first hear signal from inside the planet, your mind imagines something emerging, like a heartbeat growing louder, like machinery spinning up. But in truth, the signal is not emerging. It is circulating, passing through, completing cycles and fading, only to be gently re-excited by the next set of waves. It is process. So not buildup. You lie there comfortably supported by the crust, knowing that beneath you the mantle flexes by microscopic amounts, faithfully and harmlessly. Storms will come and go. Climate patterns will shift subtly. Technology will refine measurements. Debates will polish models. And every 26 seconds, another oscillation will complete. Not as a threat, but as a testament to the planet's remarkable elasticity. The strange signal is still coming from inside the planet right now. But now you understand something essential. It is not growing, it is not warning, it is not waiting. It is simply the sound of energy moving through a resilient world, and that world is holding you safely, exactly as it always has. And so you arrive here, back where you started, but seeing the ground beneath you differently. At the beginning, how the phrase felt sharp, a strange signal, from inside the planet. Right now, it carried the weight of secrecy, the hint of something awakening beneath your feet. But now as you rest in the quiet understanding of it, the phrase feels almost gentle. Yes, the signal is real. Yes, it is coming from inside the planet. Yes, it is happening right now. And it has been happening for as long as wind has moved water across ocean basins. You imagine the Atlantic tonight, swells crossing in long arcs, waves meeting over the continental shelf off West Africa. Pressure pulses descending rhythmically into the seabed, the crust flexing by nanometers, elastic waves radiating outward, slipping through mantle layers shaped billions of years ago. A natural mode responding, subtle, patient, precise. Every 26 seconds the cycle completes. No escalation, no hidden engine revving, no subterranean countdown, just resonance. Here's one final grounding fact. Earth's normal modes are mathematically predictable based on its size, density distribution, and elastic properties. When measured frequencies align with theoretical predictions, it's confirmation that our models of the planet's interior are remarkably accurate. The 26-second mode is not an anomaly. It's a validation. The planet behaves the way physics says it should. Historians still argue whether future refinements in Earth models will shift the precise calculated value of certain modes by tiny fractions of a second. But that debate is about decimal points, not danger. A quirky thought floats through your mind. If Earth had evolved ears sensitive enough to detect its own hum, would it find the sound comforting? A steady reminder that atmosphere, ocean, and rock are still in conversation. A planetary lullaby generated by sunlight and wind. You feel that lullaby now, not physically, but conceptually. The crust beneath you is not rigid silence. It is gently alive with motion, too small to disturb you, too steady to frighten you. And there is something profoundly reassuring in that steadiness, because the signal does not care about headlines. It does not fluctuate with human anxieties. It does not accelerate when you read about it. It simply continues. Every 26 seconds, another quiet compression and release, another ripple through mantle stone, another line traced by a patient seismometer. You picture a single instrument somewhere in a quiet vault. Its digital display scrolls slowly. A faint peak rises and falls at 0.038 hertz. The room is dim. No alarms are sounding. No red lights are flashing. Just data, steady and unremarkable. The extraordinary thing is not that the planet hums. The extraordinary thing is that you can know it hums. That satellites orbit overhead measuring storms. That ocean buoys record wave heights. That fiber optic cables sense tiny strains. That seismometers detect nanometer motions. That scientists compare notes across continents. That curiosity connects it all. And now that you are aware of it, the strange signal is no longer strange. It is familiar, predictable, almost comforting. You lie there supported by a crust only a few dozen kilometers thick compared to the immense mantle below. Beneath that, molten metal swirls quietly in the core. Above you, the atmosphere moves in slow planetary patterns. Oceans rise and fall. Winds travel. Energy flows. And through it all, every 26 seconds, the Earth completes another elastic breath. Not because it is restless, not because it is unstable, but because it is dynamic and beautifully structured. Let that idea soften your thoughts. The ground is not a rigid slab in a silent void. It is part of a living system of motion, measured, damped, balanced. The signal continues beneath you right now. And it is nothing to fear. It is simply the sound of a planet being itself. Now let the pace slow even further. Imagine the Atlantic at night, moonlight scattering across long swells. The waves are no longer dramatic, just steady, rolling, patient. They meet gently above the continental shelf, pressing down in soft, rhythmic pulses, The seabed flexes by the smallest imaginable amount, like the faintest exhale. Far below, when the mantle receives that motion and carries it quietly onward. No cracking, no strain building, just elastic response. Compression, release, return. Every 26 seconds. You don't feel it. You don't need to. Your body is tuned to larger motions, footsteps, doors closing, wind against windows. The planetary hum lives far beneath your senses in a range reserved for stone and steel instruments. And that's okay, because not all motion demands awareness. Some rhythms are simply part of the background of existence, like your own breathing when you're not thinking about it. The earth has its slow breaths, the ocean has its steady pulse, the atmosphere has its circulating currents, all of it intertwined. Let your thoughts follow one last cycle. A storm far away pushes wind across water. Water lifts and falls in long arcs. Waves intersect near a quiet coastline. Pressure pulses descend. Rock flexes. Energy travels. A natural mode hums faintly. And then, gently, the motion dissipates. Only to begin again. There is no urgency in it. No warning hidden inside it. Just continuity. The strange signal is still coming from inside the planet right now. But now you know what it is. A quiet, persistent murmur, a planetary resonance, a reminder that beneath the stillness you feel, the world is softly, steadily alive. Let that steadiness settle into you. The ground is holding. The planet is balanced. The rhythm is calm every 26 seconds. And you can rest easy on top of it.